Hey there, and welcome to this explainer. Okay, so today we are taking on a really fascinating challenge. We're talking about optimizing a digital student. And, we're not just programming this thing to blindly memorize facts. We are literally teaching a machine to actively think, to sort, and to learn from some seriously complex data. So let's jump right in and unpack the mechanics of classification and prediction.
All right, let's dive into this. We've got 5 core building blocks to cover today. First, supervised learning basics. Then, the sorters, classification. Third is the fortune tellers, prediction. Fourth, we'll look at the report card, evaluation. And finally, number 5, the power of teamwork.
So, Section 1, Supervised Learning Basics.
Basically, a supervised learning algorithm is a method where a machine is trained on well-labeled data. Think of it kind of like holding up flashcards for a kid, right? You say, this is an apple and this is an orange. But the ultimate goal here isn't just to understand a theory. We want to actually apply these algorithms to real-world data sets so that our digital student can navigate reality completely on its own.
Moving on to Section 2, the sorters, classification.
Now that begs a pretty massive question, doesn't it? How do machines actually sort data? I mean, when you throw thousands of scattered data points at a computer, how on earth does it know what goes where? Well, let's quickly break down the 3 main classification methods our machine uses to get this job done.
The very first method is decision tree induction. This uses attribute selection, measures, and tree pruning. To put it simply, this is basically a giant machine speed game of 20 questions. The algorithm looks at a piece of data and fires off a series of yes or no questions. Like, is it red? Yes. Is it round? Yes. And at each branch, it narrows down the options based on those attributes until it confidently sorts the data into its final bucket. And that tree pruning part, that's just the machine trimming away the useless questions so it doesn't get bogged down or overly complicated.
Next up is Bayesian classification, and you'll usually see this highlighted by the naive Bayes classifier. Now, unlike the strict yes or no branches of a decision tree, this method is all about probability. It sorts data by calculating the absolute likelihood of an item belonging to a certain category, entirely based on prior knowledge it's already gathered. It's kind of like the machine saying, well, based on the 500 red, round things I've seen before, there's a 95% chance this brand new thing is an apple.
Our third classification tool is called K-nearest neighbors, or KNN for short. And honestly, this is a wonderfully intuitive method. It categorizes a new unknown data point just based on its proximity to existing, already categorized data. Think of it like literally asking the people next door. If you drop a new data point into a neighborhood on a graph where all the surrounding points are apples, well, the algorithm assumes this new point is probably an apple too. It literally looks at its closest neighbors to figure out its own identity. How cool is that?
So the crucial point here is understanding the major shift we're about to make. Up until now, we've been talking all about classification, sorting data into distinct, discrete categories like apple or orange. But prediction is an entirely different beast. Prediction is all about estimating continuous variables and future trends. We aren't just sorting things into buckets anymore, we're actually forecasting numerical values. We are asking how much or how many.
Which brings us to Section 3, the fortune tellers, prediction.
To predict the future, our machine needs a highly specific framework, and that framework relies completely on the structure of regression models. Regression models are basically the mathematical engine, the crystal ball, if you will, that our machines use to act as these digital fortune tellers. They look deep into historical data structures to draw a reliable mathematical path forward.
And the most fundamental version of this is simple linear regression. This is a predictive model that estimates the relationship between a dependent variable and one independent variable. Basically, imagine just drawing a straight line right through a scatterplot of data to find the overall trend. Grasping this concept is absolutely vital because it's what allows us to analyze and interpret the prediction of dependent variables using exactly these kinds of straightforward linear models.
Moving right along to Section 4, the report card, evaluation.
Okay, this is where metrics like precision and recall come into play. These are specific error measures used to validate the functionalities of a model and to find its true accuracy. And why does this matter so much? Because rigorous evaluation ensures our digital student isn't just out there making lucky guesses. Precision tells us exactly how many of the items it labeled as positive were actually positive. And recall tells us how many of the actual positive items it successfully managed to find. It's a really rigorous check on the machine's actual competence.
Now, to effectively test the machine, we follow 3 key steps.
Step 1. Split your data using holdout or random sampling. You literally have to hide some of your data from the machine during training. I mean, if you don't hold out test data, I guarantee you the machine will absolutely cheat. It'll just memorize the answers instead of actually learning the underlying patterns. Step 2. Test thoroughly using cross-validation. This rotates exactly what data is hidden to make sure the model is robust across the board. And Step 3. Refine using bootstrap methods, which involves sampling with replacement to get incredibly stable estimates. We have to implement these exact steps to actively improve and verify the performance of our models so they are truly bulletproof.
And that brings us to our final section, Section 5, the power of teamwork.
All of this brilliantly illustrates a really beautiful concept in machine learning called ensemble methods, specifically bagging and boosting. This is all about combining multiple weaker models to create one super accurate, unified prediction. Bagging has different models independently vote on the outcome, which smooths out random errors. Boosting, on the other hand, forces new models to specifically focus on correcting the mistakes made by the previous ones in the chain. It is literally teamwork in its purest mathematical form.
Now, if you want to keep pushing your digital student to the next level, here are the self-learning topics you definitely need to tackle next. Random forest, which is basically an ensemble of decision trees. SVM, or support vector machines. And then you'll want to expand those predictive skills with multiple linear and logistic regression. Think of this as your ultimate roadmap for upgrading those machine learning skills even further.
So as we wrap up this explainer on classification, prediction, and evaluation, I want to leave you with a thought. We can literally teach machines to categorize incredibly complex data, and we can even teach them to predict the future using mathematical models. But will their accuracy ever truly reach 100%? As we continue chasing lower error rates, tweaking our ensembles, and demanding higher and higher precision, it's a really fascinating question to ponder. Keep learning, keep questioning, and I will see you in the next explainer.